Hello everyone. In this video, we will look at how to do power, energy and charge calculations for an ideal basic circuit element. We will discuss the systematic procedure for doing such calculations in a confident manner. Recall that an ideal basic circuit element is not a real-world component. It is in fact an important circuit theory abstraction, and it is used to model real-world components and systems in circuit analysis. The theory behind the ideal basic circuit element is discussed in other videos in this channel. The link is provided at the end of this video. When an ideal basic circuit element has DC voltage and current as input, we can easily solve it completely. For given values, we can determine the charge flow direction, voltage drop or rise between the terminals, whether the element is absorbing or supplying power, and whether electrons passing through the ideal basic circuit element are gaining or losing energy. In this video, we will focus on ideal basic circuit element with time varying inputs as shown here. Typically, the voltage and current may be linear functions or exponential functions, or a combination of linear and exponential functions, or even a combination of exponential and sinusoidal functions. The voltage and current may be specified mathematically using exact equations, or can also be given in graphical format as plots. For such problems, we are interested in the power, energy and charge calculations as specified here. The general procedure for the solution is discussed here. This procedure is applicable for any time varying voltage and current expressions for an ideal basic circuit element. Recall that instantaneous power associated with the ideal basic circuit element is the product of the voltage and the current. Thus, to find the power associated with the ideal basic circuit element at time t1, we just need to evaluate the power expression at time t1. To find the time when the power delivered to the ideal basic circuit element is maximum, we employ a fundamental method from calculus. We differentiate the power function and set it equal to 0 and then solve for time. Recall that the derivative of a function at a point along the function is equal to the slope of the tangent line at that point. At a local maximum or minimum, the slope is 0. Thus, solving this equation gives us the time at which the local maximum or minimum occurs. We can then plug the time values back into the power expression to check which gives the maximum value. Recall from basic physics that power is energy per unit time. Thus, to find the energy delivered to the ideal basic circuit element between time 0 and time t2, we need to integrate the power from time t0 to time t2. To find the total energy delivered to the ideal basic circuit element, we integrate the power from 0 to infinity. Finally, recall that current is the rate of flow of charge. Thus, to find the total charge that has accumulated at the upper terminal 1 of the ideal basic circuit element at time t is equal to t3, we integrate the current from time t0 to time t3. For illustrating the calculations using this systematic procedure, consider this first example where the current is an exponential function and the voltage is a product of linear and exponential functions. We can use any software such as Mathematica or MATLAB or Python to plot the voltage, current, and power in this case. We can see that the current is an exponential function. The voltage first increases due to the linear part and then decreases due to the exponential part. The instantaneous power in this case is also an exponential function and has a maximum value at time t equals to 0. The complete mathematical solution is illustrated here. In this case, the maximum power occurs at time t is equal to 0 seconds and has a value of 50 milliwatt. Also, the total energy delivered to the circuit element is 62.5 microjoules. Please pause the video now if you wish to study the solution in more detail. All the calculations for this first example can be easily carried out using a programmable or graphics calculator. The details are shown here using a common programmable calculator software. In particular, note that we can find the time at which maximum power occurs directly using the solve and differentiation commands. We can carry out all the integrations and also use this command to show the final answer in decimal format when required. We can also configure the settings to display the values in engineering format. The values shown here match the values shown previously. Please pause the video now if you wish to study this calculator solution in more detail. Finally, let us consider a complicated example. Here the voltage is in kilovolt. Both voltage and current are products of linear and exponential functions. The plots for the voltage, current, and power are shown here. In this example, all the three variables first increase to reach a maximum value and then decrease. We can see that for the power, the maximum value occurs at a non-zero time value, and this is different to the previous example in this video. The complete mathematical solution is illustrated here. In this case, we get two solutions for the time, and the maximum value of the power occurs at time 2 milliseconds and has a value of approximately 695 milliwatt. Also, the total energy delivered is 2.4 millijoules. All these calculations can be carried out using a programmable calculator. Please pause the video now if you wish to study this in more detail. We can also use Python to solve such problems. We can define the voltage and current as functions. We can define the time vector. The power, energy, and charge calculations can be carried out using inbuilt functions. Finally, we can also plot the voltage, current, and power expressions. When we execute, we get the plots, and also we can see that the answers are the same as before. This Python script is available in the video comments section. Please make sure to study it. In this video, we have discussed how to systematically calculate power, energy, and charge for an ideal basic circuit element. The calculations can be carried out easily using a programmable calculator or a programming language like Python. The systematic procedure shown here applies to all cases, irrespective of the exact voltage and current expressions. I hope the video is helpful to your learning. Thank you for watching the video.